The method we're about to use will work for sine to the power of an odd number or cos to the power of an odd number, where the power is not just simply 1. So for instance, if you had sine to the power of 3x, or sine to the power of 5x, sine to the power of 7x, or cos to the power of 3, 5, 7, you can use this same method. And you'd start off by rewriting this as, so taking out a factor of sine x, so it becomes sine to the power of 4x times sine x. And if you were to have, let's say you're trying to integrate cos cubed x, then you do a similar kind of thing where you take out a single factor of cos x, and then you're left with cos squared x. So why is this useful? Well, what we can do is, now with the sine to the power of 4x, we can rewrite this as sine squared x squared. And that can then be written as 1 minus cos squared x. And that's just using the identity sine squared x plus cos squared x is 1. Now we can expand this out, and hopefully you should see after that why this is a good method. You can expand this out. This becomes 1 minus 2 cos squared x plus cos to the 4x, all multiplied by sine x, and then we can times this out. This then becomes, so multiply this whole bracket by sine x, becomes sine x minus 2 sine x cos squared x plus sine x cos to the 4x. And now, these two things, what we have here and what we have here, are both of the form of f dash x multiplied by f of x to the power of n, where n is not equal to minus 1. If they're in that form, the solution would be of the form of f of x to the power of n plus 1. So just to clarify, the reason why this is of that form is because f of x, which in our case would be cos x, would differentiate to make minus sine x. This is not quite minus sine x, it's off by a factor, but we'll correct for that. So cos x is our f of x, sine x is our f dash x, and the 4 is the power that we have here, which is not minus 1. So our solution for this would be of the form of cos to the 5x. So what we can do is we can differentiate this to see what corrective factor we'd have to put in front. Use the chain rule. Y is equal to u to the 5. U is cos x. Find out what dx is. So this differentiates to make 5u to the 4, and then cos x differentiates to make minus sine x. So let's just tidy this up. This becomes minus 5 sine x u to the 4, which is cos to the 4x. So this has differentiated to make this. It's not quite what we have here. It's off by a factor of minus 5. So we can multiply this by minus a fifth, and then that will carry through to the end to cancel out with the minus 5 that we have here, and now this differentiates to make this. So that part would just be minus a fifth cos to the 5x. Put an equal sign here. This bit is minus a fifth cos to the 5x. And for this part, the sine x, that just integrates to make minus cos x. Then there's this bit here. So we'd follow a similar kind of procedure. So the solution to this would be something of the form of cos cubed x. If we differentiated this, again using the same method as above, we'd end up with, so the 3 comes out, a copy of the 3 comes out. We have to differentiate the cos as well, which is minus sine x, and then this gets reduced by 1 power, so multiplied by cos squared x, or minus 3 sine x cos squared x. We want it to be minus 2 in front. So we want to get rid of this minus 3. The minus is fine actually. The fact that we have minus is okay because we want minus there. So we can keep that. We want to get rid of the 3. So let's divide by 3. And then we want to introduce this 2. So we can times by 2. So timesing by 2 over 3, the divide by 3 gets rid of this, the times by 2 will then introduce the 2 that we want. So times this by 2 over 3, those two 3's cancel out, and we get what we have here. So then, this here is the integral of that term, positive 2/3 of cos cubed x. So plus 2/3 cos cubed x minus this plus c, and that will be our final answer.